please welcome to the stage, Aman.
Hi everyone, thank you so much for the warm welcome. So I'll be talking about simplifying building consistent systems using Differ. So my name is Aman. I'm a senior software engineer at dgraph Labs. dgraph is the company that is building graph databases. So we build a graph database. It's written in Go and it's written from scratch. We are the author for Badger and Strato, if you're familiar. And I have been writing Go code for 7 years or so. Before dgraph, I was working for a networking company. We were building backend applications there. And before that, I was working for a data company. And so all of this talk is actually what I've learned over 7 years in building systems and also writing Go code. So I'm really excited to be here. Okay, so this is the agenda for the talk. I'm going to start to give you some sort of sense as to how I use Differ in different contexts. Then we'll jump into the idea of consistency and what are consistent systems. And then we'll define what consistent systems are, and then how do you see consistency problems in the systems that we build every day. Then I'll quickly talk about why you should care about building consistent systems again, and then how to build those consistent systems. And then we'll finally see how we can use Differ to simplify building consistent systems. So let's jump into Differ. So Differ in Go. So I am assuming everybody has used some level of Go code, and if they have used Go code, good chance you have also used Differ. So I'll just give you a series of examples of how we use Differ. This is one example. So if you open a file, you can quickly close it. You can quickly write the Differ statement to close the file. And I love the way, like this. I was seeing Nick writing double quotes, and he missed with double quote with a single quote, and that gave an error on the command line in the last talk, if you notice. And same thing with when you're writing code, you open a file, but then you forget closing that file, and Differ allows you to make sure that you close the file right away, at least write the statement. And the way Differ works is that the whole function gets executed, and then at the end, the Differ statements are executed, right? So in this case, I open a file in line number 11, and then I check the error if the file was actually opened, or line number 15 is when I close the file. I write the statement for closing the file towards the end, and then I can write all the code related to the data in the file. Okay, so this is just one example. This is one more. So I don't actually do this, the last slide, because the close function returns an error, and you want to handle that error, whatever like makes sense to you in the situation. So in this case, I just want to log the error in case closing the file fails. So we should really avoid just calling close or something equivalent. We should also handle the error that gets returned. Okay, this is for logs. If you acquire a log, you want to write a Differ statement for releasing that log, and then you do whatever you want to do after that. Right? Again, really simple, really useful and use case of Differ. This is another really good example of Differ, I think. So whenever you're writing an HTTP handler, the first thing you want to do in that handler is close the body of the request that you get. If you don't close it, that's a really major problem for memory leak. Right? So first thing I always do in a HTTP handler is close the body of the request. Then you read the body, and then everything else you want to do after that. This is for context. Again, really simple and very useful. If you create a context, you want to call the cancel right away, or you want to write the Differ statement for cleaning up the context right away. And then you can see that line number 185 from the top. And then again, really useful to, if you forget cleaning up, again, this is going to be a thing where memory leak shows up in your program. Below, if you notice, there's another use case of Differ. You create a new transaction. You want to right away again say transaction.discard, and then write that in a Differ statement. And then if you notice again, I'm handling the error, not ignoring the error that is returned by the discard function. This is again line number 191 to 201. Make sense? This is one of my favorite use case of Differ. So you have a function, and you want to figure out how long this function took to execute, right? So line number 179, I see what's the current time right now. And then you write the Differ statement. You calculate how much time it took. You use time.since. Line number 180 is where I'm looking at now. And then Differ will be executed towards the end of the function, and it will print how long this function took to execute. We use this a lot in dgraph, especially when we are doing query processing. right? This is like, I thought, when I saw it first time, I thought it was really cool. This is for recover, again, very standard use case. This is one of the reason differ was designed. So if somebody, so again, we use it really, like, I think this is another really cool way of doing it. So this is for our first test for our query parser. So we call the parse function at the below in the box, line number 40 to 49. And so the invariant for our first test is that the parse function should not panic. It shouldn't do anything bad, right? And the way we write our test is we call the parse function. So because the first test, we'll get really random strings as our query. And then it is possible that we return an error. Maybe it's a reasonable query and we are able to parse it. But in either case, it should not panic. That's our invariant in our first test. And so we write a differ and do a call recover. So if there's a panic, we'll call recover. And then we'll know that there was a panic and then we'll fail our test. Because whenever you're writing a first test, it's really hard to figure out what your invariant is going to be. Invariant is basically something that you want to make sure. So when you're writing first test, because these are random inputs, you don't know what output is going to be. So you cannot compare the expected output with the output you get from the function return. So you just build these invariants, which you know that this will never happen. In our case, panic should never happen. And then this is probably second last use case. So this is for tracing. So again, very similar to the idea of execution time. Tracing, we use open tracing and Jaeger, and this is again for distributed tracing. And what we do is we create a span, and then we calculate how long it took. We attach all the text. This is line number 95 and 96. So we calculate how long it took to execute this function, and what are the tags. We are associated those two things. And then we do it in the differ, so it will be done when the function is done executing. I don't think Go is the only language where something like differ exists, and it should have been there like from the initial like C or C++, right? I think Rust is trying to do it, but I'm still not sure. Okay, so again, this is the base, and now we'll go into the second part of the talk, which is consistency, and then we'll put them together into building consistent systems using differ. So what is consistency? And I think this is something, whenever I try to build a new system, a new application, the first question I'm like, oh, this has to be consistent. But I've never really asked myself, what is consistency? So I Googled, and then this is what I found. So consistency is something, it always behaves in the same way, has the same attitude, and achieve the same level of success. The idea is that it's gonna remain the same. It's not gonna be unpredictable, right? So if I took the same approach towards systems, computer systems, this is what I come up with. So behavior for a computer system has to be well defined so that you can predict its response and deal with it, right? So what we do when we build an application, we talk to another system, we expect a certain response, and then we handle that response. That, oh, this is a good response, we're gonna use it. It's a bad response, we're gonna handle the error, and so on, right? And so if you cannot define what your system is going to do, you cannot deal with it. And if you cannot deal with it, something bad will happen in your system. So this is what we're trying to achieve, and I'll give you some examples now and the point here is to only show you that we don't think about consistency while we are building systems, but it's truly really important to think about consistency when you're building systems. And then I'll show you why it is that important. I'm not gonna show you how part I'm gonna skip a little bit. I'm gonna focus on the importance of it. And you will see, I'll take some examples of systems, and then we'll see like how it is important. Again, consistency is a very loaded term. It's used in different contexts, but whenever you're thinking about your system and your application, you define what consistency means to you, right? It's not defined by, so if I am building a database, then I say, hey, this database will give you read after write, right? So if you write and then you read, you will get what you just wrote, right? And I can define whatever I want. Consistency does not mean it has to be very, very consistent, right? And so I can say, hey, no eventual consistency. Anything can happen, no guarantees. That is also a consistent system. The definition is, it has to be well defined. That's really crucial. Okay, so let's jump into examples, right? So this is again, whenever somebody says consistency, people think about ACID. So I'm gonna take example of ACID. ACID is atomicity, consistency, isolation, and durability. And that's used a lot in databases. So what does consistency mean for databases? right? So this is again, if you're using a database or you're building a database, you should think about consistency at that point. And again, the very standard example of this would be S3. Everyone probably have used S3, and then you would expect, hey, I just wrote a file into S3, I should be able to read it, right? And that's what I thought too. And we built a data pipeline. Our pipeline wrote to S3, and the next step of that pipeline read from S3, and it didn't find the data one of the days. And I'm like, how is that even possible, right? Because I did not think about that S3 is eventually consistent and data may not be there. Right? So for databases, or again in data stores in general, this is how I define consistency. So databases have transactions or operations, and each transaction or an operation can only bring the database from one consistent state to another consistent state. There's nothing in the middle, right? And again, all of these consistency ideas are important, and like they become more relevant when something is happening in parallel, right? So for example, if transactions are happening in parallel, you want to make sure that nothing bad happens. It goes from one consistent state to another consistent state. And let's see an example. So this is a small database. It has two keys and values. One is count and another is updated at. And so count is 10, let's say, and updated at is September 20th, 8 a.m. So I set count to 10 at September 20th, 8 a.m. GMT. Now I do an increment. This is an operation that I did, and count now becomes 11, and that was updated at 9 a.m. GMT, right? Everything makes sense at this point. But let's say I do a read now. So I'm like, oh, what's the value of count and when was it last updated? What if I get this? The count is 10, which is the older value before I did the increment, but updated at is 9 a.m., right? So this is weird, right? If I'm like, oh, I did an update, it was 11 at 9 a.m., not at 8 a.m., right? So it should be 10 and 8 a.m. You can see, notice this in this slide. So 10, 8 a.m., 11 at 9 a.m., right? But what I got is 10 at 9 a.m. That's weird, right? We don't expect that to happen in our case, right? Because the way count and updated at are related, right? If they were completely like they were not related, like count or another count, it's fine. The values could take different values. But if they are related, that's where it matters. Right? So this in some cases it may not be acceptable. In some cases it may be acceptable. So we'll see like why in some cases it is acceptable and in some cases it is not. Right? Okay, so this is just one example that could happen with databases. There are so many other problems that could happen. You could do a dirty write, meaning there are two transactions running in parallel. One did a write and somebody did an overwrite, and you don't even see that write that happened before. And again, I'm not going to go through all of them. You want a consistent view. There's a really cool algorithm if you want to understand consistency really well. It's called Lamport-Chandy algorithm for consistent snapshots, and it'll really help you understand what consistency is in databases. And so that also sort of defines what consistent view of a database is, of a data store is, right? And it will also define this that, hey, this is not allowed. But again, I'm not saying this is not acceptable. I'm just saying in some cases, it may not be acceptable. We define what consistency means to us for our application that I'm building, right? That's really, really important here. And that's why I think the word consistency becomes really confusing because everyone defines it different, which is perfectly fine. Okay, so all of these problems can happen, and because of these reasons, we have these so many different versions of consistency that a database can give you, right? So dgraph, for example, is snapshot isolation, one on the left a little bit. That's what dgraph gives you. Again, it has a definition, it has meaning, and then you can, if you're using dgraph, you have to be careful and assume that it only gives you snapshot isolation, not stronger. So top ones are stronger. As you go lower, they're slightly weaker. And stronger and weaker means that stronger will have like fewer histories allowed, but let's not go into that. It'll just be more complex. But the idea is that if you're building a database or using a database, you have to understand what is the level of consistency that gives you, right? And that's how you should build an application. For example, if you're using S3, you should be careful that maybe just a write, but you may not be able to find that file a few seconds after. So you want to put that in a loop and then try again a few times. But if you're using dgraph, you don't have to do that. If you do a write and you do a read after, because it is snapshot isolation, you'll get that write that you just did, right? So this is the problem here is that we don't think about these scenarios when we are building an application or a system. And this is what is crucial here. Okay, so we talked about databases. Let's take more examples. Data pipelines in big data, right? So for data pipelines, this is how I define consistency for data pipelines, that all the data stores should be updated in such a way that they do not provide inconsistent information. You'll find it funny because I'm defining consistency using the word consistent, right? But again, you will see what it means. So again, this is a data pipeline. There are 4 steps, 1, 2, 3, 4. Second one is writing to S3. I'm calling it A. And then fourth one is writing to B. That's a database, let's say. And this is a pipeline that runs, let's say, every day. And there's some data that comes every day. You process it and then finally write to these 2 stores, the S3 and database. Okay, let's say what happens if step 3, one day step 3, something goes wrong and step 3 crashes. Like when the pipeline is running step 3, it fails. So now what happened in this case is that we updated the data on S3, which is A, not in the database B, right? And now these two will not have consistent information, right? And that again may be a problem for an application that you are building, because you read from A and you're like, oh, this user exists in A, but how come it does not exist in B? That's really odd, right? Another problem that could be that you rerun the pipeline thinking that, oh, step 3 failed, I'm just going to rerun the whole thing, right? Now, let's say step 2 created a directory on S3. You'll try to create it again and it'll fail, right? So again, thinking about these things is really crucial, that, hey, what if each step fails? What do I do then? Let's say somebody noticed that step 3 failed. Let's say nobody noticed for a day or 2 or 3, right? It's going to remain that way for that duration, right? So you can always exaggerate the problem and realize that it actually could be a problem for you and for your application. So this is for big data. Let's go, and you're serving an API request. How do you define consistency then? So this is how I think of it. If there's a request that comes and I'm handling that request, I'm writing code for that. Either we execute the whole thing or we do nothing at all, right? It cannot be that request is like half handled. That's not acceptable, right? And again, from a consistency standpoint, responding back is actually not crucial, right? Responding back is important from an availability perspective, not from a consistency perspective, right? This is again the CAP theorem, if someone can recall. Okay, so I learned this today itself. It's a really cool example. This is called outbox pattern. And so let's say there's a request coming in and there's a REST API. What happens is that this REST API writes to a database and also pushes a notification to event bus. And now think about this, that I wrote to the database, but I crashed or something went wrong when I wrote to the event bus. So now this is an example of an inconsistent system, that my database is updated, but the notification is not there. And again, this is a solution, but that people use something called Outbox and do a transaction and a publisher and then solve this problem. But again, focus on the problem, that if you don't think about this, this could happen in your application. Okay, one last example. And again, this is in dgraph. This still exists. I saw it like maybe a weeks back. I haven't fixed it yet. But let's say you're writing to disk. How do you define consistency then, right? And so the way I define it is the data on disk should always make sense, right? No bad data, no corruption, no incomplete written data, right? Whatever there is on the disk, it has to make sense. Okay, so I'll give you an example. And I'm not sure it's a problem in dgraph yet. I've not seen it, but this is how it happens in dgraph. So we have so if somebody is familiar, there's something called wall, write-ahead logs. And we have a write-ahead log in database. We also have a file that explains all the files in write-ahead log. We call it wall.meta. And it has something called some data. And this is how we write that data. So we have the first 8 bytes or 4 bytes is the length of the data. So I'm writing it 100 now. And then the 100 bytes, right? So this is how it's laid out in the file wall.meta on disk. Now let's say I'm like, oh, we need to update this data, and the length of it now is 200. So what I do is I'm going to write 200 first. So I'm going to say first 8 bytes, update those to 200. So I did that. And then I'm going to write the 200 bytes that come after. But right before I could do that, right, my system crashes or something goes wrong. This is the state now, and my system crashes, it restarts and it reads this file and like, oh, there's a 200 length data that I should read, and it tries to read it and it's going to end up reading some garbage, right? So this is again a really simple example of an inconsistent state of our application. Right. So consistency sort of shows up no matter what application you're building, because you'll be writing to a database, you'll be writing to a queue, you'll be building a microservice, you'll be writing to disk, something of that sort is you're going to be doing. And again, what I have talked about today is only data consistency, which is again really crucial to our applications. So okay, so why you should care, right? So I mean, simple reason is because the systems that you want to build should be correct, right? They should be well defined. Somebody using them should not be confused as to like, oh, what's going to happen, right? It should be a well defined system. So again, this is the crux of what I have explained, that every system that we have, that we build, has to be a consistent system. This is like a requirement that everyone should follow, and its behavior has to be well defined, and this is essential for building correct systems. And again, it's really, really important to build correct systems, right? I think correctness should be like 100, like that's a no-brainer. Nobody should build incorrect systems. That's like obvious, but I think we don't do that ourselves. I have built incorrect systems myself, right? So it's not something that, but again, that's what we should strive for. Okay, so all of this makes sense, but how do I build a system, right? And so I'll just give you a few ideas. Again, this really depends on what you are building and how you want to sort of fix it. There could be multiple solutions to the same problem. So again, what you want to do is, when you're building a system, you want to identify all possible states that a system can be, and ask yourself, hey, is this an acceptable state to be in? If this is acceptable to your application, that's fine. It's a consistent system. If it is not, you want to fix that, right? And then this is a little exercise that I do every time I'm building something. If I have a piece of code, I say, hey, what if my system crashes right after this line of code? What if my system crashes in the middle of executing this line of code? Right? So you ask these questions yourself and see like, oh, how is my system going to recover from that situation? If you do that exercise yourself, you're mostly good to go. So again, take your system, break down into small steps. Each step has to be atomic, and we'll see like an example using differ. It'll be really cool. Each step has to be idempotent. Again, atomic and idempotent, and they'll give you most of it what you want. But again, it's not easy to have atomic steps. That's the hard part. And if you ensure that, you will have a consistency point after each step, and you're good to go. So finally, what if I don't have atomic steps, right? What if my steps like multiple steps? Let's say I get a request and that is supposed to do two things, write to database and also to a queue. Now it's not atomic anymore, right? So what do? You can use differ in those cases, and it will help you build consistent systems. So let's build one, right? So this is an example. So this is, again, I think 2016 is when I came across this. And this is, I thought this whole thing started in 2016. I thought it was a really cool use case of differ. And so this is a problem that I was solving then. If somebody knows OpenStack is a way to build cloud yourself on-prem. And there's a service called Cinder. Cinder manages all the storage in OpenStack. And we were building a manager for managing OpenStack. Right? So you build a service that could manage Cinder and then add and remove new storage to it. Right? So again, just to, like, the important thing here is, you get a request and you are supposed to execute 3 steps. One is write to etcd, because what if my system, like everything goes down? Etcd will still have my configurations. I can recover from that. So whatever configuration we get for Cinder, we write to etcd. Etcd is a key value store, distributed, highly available, and all the cool things. I still have time, right?
How many slides left?
It's 2-3 more. Okay. How much time do I have? 5 minutes. Okay, got it. So first step is write to etcd. Second step is update the configuration for the service. So service reads from a file on a disk. So I'll update that. And third step is restart the service so you can see the new configuration. These 3 steps, supposedly atomic. And then if I ensure that they're idempotent and everything, and then my small part of the application is at least consistent, right? So 3 steps you're going to do: write to etcd, update the configuration on disk, and then restart. Right? So we'll see some code quickly. So I built like a toy example to show you this. Let's see if I can. Okay, this is fine, right? Okay, so I'll just quickly show you how I wrote the code for it and then how I fixed it. Okay, it's visible, right? Okay, so again, 3 simple steps. First step is write to etcd. So I'm just doing some etcd operation, and then I just say this is a key, this is a value. Step 2 is write to file. Again, really simple, nothing really interesting here. And then restart our service. right? Simple code, everything works, but does it, right? Let's say write to file fails, right? Something went wrong with the disk is full, and then you cannot write to file anymore. What will happen is we updated etcd, but we did not update sender with the new configuration. In that case, your system is inconsistent now. etcd has a different configuration, whereas sender is running with a different configuration, right? So that's really bad. And now comes the cool part. So the way you fix it is you use a boolean and you use a defer. So again, same 3 steps: step 1, step 2, step 3. Yeah, there it is. So this is step 1. If you look at the code step 1, I'm doing the same thing that I was doing before in etcd, but you write a defer. And then you put a if condition with a success variable, boolean variable there. And you say, hey, if not success, undo step 1. Right? And again, undo step 1 would basically restore the old configuration. You do the same thing with step 2 too. You write to the file, but then you say, hey, if not success, delete the file. Right? And same thing with step 3. Finally, but we don't have to write the undo step because this is last step. If it fails, we don't care. So now what will happen is success was initially set to false at the top, right? Now we'll execute step 1. Success is still false, everything went well. Let's say step 2 failed. So now at this point I failed. What will happen now? There's going to be an error and we start executing the defer. And at that point success is still false. So this will become true and we undo step 1, right? And it'll undo as if nothing happened, right? But let's say everything succeeds, we'll set success to true, and all of the if conditions will become false, and we don't have to do anything. Everything works, right? So this is again, I thought this was really cool, and the coolest thing is if you had to do it without defer, it will be such a challenge, such a pain, right? If you have to add one more step, you'll just add step 3, undo step 3, and you're done. You'll step 4, undo step 4, and you're done. You don't have to worry about, oh, what if the step 3 fails? I have to undo step 2 and 1, but step 4 fails, I have to undo 3, 2, 1. You don't have to worry about all that stuff. Right, just final slide. So yeah, this is just the code that I showed, and some of the references where I took a lot of these ideas, and that's all. Thank you so much.